All right. So, in our previous session, we learned about basic statistical tests like t-test, a Wilcoxon test, and the assumptions behind a t-test being when you're testing two groups. T-test assumes that you have normally distributed data within the two groups that you're testing, and t-test gives you a p-value for how different the two groups might be, two groups might be, and their means, how different the means of, or the average. Whenever I say mean, it's the average for, usually in the statistical language, they call it a mean. So for a t-test, the assumption is populations being normally distributed, and for a Wilcoxon test, you can forego that assumption and basically use any data. Therefore, most of the statistical testing we do is with the Wilcoxon test. And so there are much more statistics that are involved with more complex models, and in this course, I'm just going to cover some of the basic statistical modeling. We will not go into more complicated modeling, but today's session will concentrate only on two models, which is analysis of variance and linear models. So just for the first thing, I'm going to start with the analysis of variance modeling. So therefore, I just have an excerpt from Wikipedia on the right-hand top corner here, which says analysis of variance is a statistical test, and it tests whether or not two means of not just two, but means of several groups, whether they are equal or not. So you use a t-test to compare two groups and whether their means are different. But you use an ANOVA analysis of variance testing if you have more than two groups or several groups. So this analysis of variance gives a measure of whether the means of several groups are equal or not. So, and one more major variation for analysis of variance model and other models like linear model is you will start using a categorical predictive values for predicting a response variable. So this nomenclature might be new, and generally in modeling what we are trying to do is you have a response variable, which is the output variable that you're trying to predict based on a set of data. So like in our MPG, the empty cars data set, we are trying to predict mileage, gas mileage based on various factors, right? So various factors being the number of cylinders, whether transmission or what's the other factor? Yeah, transmission, and you have weight and lots of other factors in that data set. So if your predictive variables are a continuous variable, like when you're trying to predict the gas mileage with weight is sort of a continuous variable. You cannot put it into different categories. Of course, it depends on what you're doing and how large is your data set. If your data set has only like 4 or 5 cars which fit into say low like less weight, medium weight, and high weight, you could maybe categorize them into 3 categories depending, and give them labels depending on what you want to do. So that way you can categorize it. But weight of a car, if you have thousands of cars worth of data, then it's a continuous variable. You start with, maybe I'm just guessing, maybe 500 tons to something like 10,000 or so. I'm just guessing, so I don't know the weight of cars. But so it's a continuous variable, and different cars will have different weights. So in that case, you will be using a linear model. But ANOVA specifically is used for when your variables are categorical variables. So we'll see one example here, which is the insect sprays data set. So this is one data set that is already included in your built-in data sets. And this is a very simple data set. Like what you have is insect sprays, and you have one variable called count and the other variable called the spray. So basically, the count is the number of bugs. They were basically doing an experiment, and they were counting the number of bugs that are present in each square area or something like that, depending on what spray they use. So they have like it's a factor variable with 6 levels. So there are basically 6 different types of insect sprays they are using, and then counting the number of bugs. So I think they start off with the same number of bugs, and they spray it and spray this and see, give it some time and see whether the bugs have died or not. So that's the data set and that's the experiment. There are only 72 observations. So obviously you'll see that there are only 6 sprays. So there are multiple values for each of these sprays. And basically there are different bins. Suppose they have spray A, they have used spray A not just in once. They have used it several times in different boxes, just to be able to test and take an average of that. So usually you might know this. Usually when you're conducting an experiment, you don't just do it once. You replicate, you create replicates. You have like biological replicates, you have technical replicates and things. So just you take replicates because you want to minimize the error factors that might be present. So in this data set, what we have is we have six sprays, and these 6 sprays being used on multiple boxes, and therefore we see the number of bugs present in multiple boxes, and that's the data. So we have total of 72. So just looking at the structure of insect sprays, we see that it's a data frame consisting of 72 observations and just 2 variables. Not a huge data set, so let's use this and do analysis of variance models. Specifically, I picked this one because the spray here is a categorical variable, and because it's dependent on 6 different sprays, and 6 different sprays are just categorical variable. So we want to be able to predict the count, the number of insects that you want to develop a model that will give you the number of counts depending on which spray you're using. So let's look at this model. So what we are doing first is using analysis of variance, and this is a built-in R function, AOV. So you can use AOV and give it certain parameters, and then it will create this analysis of variance model. So whenever you do this, the way you have to write your equation is use this tilde. And let me just so this count is y. So I think I showed you this in the last class, that, and this spray is the x. So whenever you're using, so why do I call it y and x? Usually, and this will be more clear in the linear model, is usually what happens is if you look at it in graphical terms, you have a y-axis and an x-axis, right? So whenever we are doing correlations or any modeling, what we do is we predict y, which is the response variable, based on the values or the predictor variable x. And therefore, in a linear model, you kind of make a plot like this. I'll tell you that when we get to the linear modeling part of this class. But in an analysis of variance model, you have you actually do it in a kind of sectional fashion analysis of variance. Suppose your data is like this, you kind of divide that into sections, and it analyzes the variance. So basically, you don't have to really know the mathematical details of how analysis of variance is done, but just to remember that analysis of variance is a means of testing different groups and whether their means are equal or not. And what we are testing in this example is to see whether the mean number of bugs present after using a spray is that same, similar, or different between these 6 sprays. So essentially, if someone did this experiment and wanted to find out which is the best spray and get some guidance on what the cost of it is according to how much you want to live with, right? So if you think that one of this performs the best but it's too pricey, you want to settle down with the second one, which might be less cost, but you might compromise on some of its efficiency. But even that, usually even in business decisions, what you do is you test you test multiple things, multiple items which are performing the same, and see the difference between them and pick the best. Even within the narrow range, even for the second best, you might feel that you might notice that there are other choices within the second best that provide competitive pricing, and if the efficiency is not compromised too much, you might go for say the second best, or within the second best level, a different one. So just to get a brief idea on which one is performing best, or pick your choice based on pricing, this kind of analysis is helpful. So in our analysis of variance model, count, the number of count is the number of bugs. That is the output variable or the response variable, and spray, the type of spray or the spray name is going to be the predictor variable, or you could call it. So there are lots of nomenclatures depending on which subject you go to. Like there are in stats, it's called response and predictor variables. In machine learning, it's called independent and dependent variables. So basically, the output variable is something dependent on these predictor variables, which are independent. But in some more complicated models, you might notice that the predictor variable, like one example is the empty cars data set, where we saw in the correlation plot that some of these are correlated with each other, meaning maybe the transmission, or the number of cylinders is correlated with something else, maybe the transmission or the weight and things like that. So each of these variables may not independently be useful to predict the output variable because they are correlated, and that comes in more complicated modeling. But let's just stick to this example of insect sprays. And once you do this AOV, which is analysis of variance modeling, and you give it the output variable tilde the predictor variable, which is the spray, obviously you have to give it the data set, which is our insect sprays. You build this model. So now the model is built based on this equation that we gave, and when you check what's in that model, you have a series of terms which you don't really have to worry about. But let's look at it in our studio. Where's my section? Okay, so this one. So I have count, tilde, spray, and I built this model. It's a simple one-liner. So in R, models really are built simply by those commands. So it's not a huge code or anything like that. Once you get used to, you would be building models just like that with one line of code. Okay, so what you got here from the analysis of variance model is what you see here. It just recalls the whole equation, and it gives you terms and it says sum of squares and degrees of freedom. So don't worry of it as yet. I am going to explain what each of these means, and this is called residuals. So it's kind of difficult, and you will not get this concept if you're listening to it for the very first time. The concept of residuals and sum of squares, it might be confusing, but if you had already known about it, it's fine. But I'll just guide your focus on to the important parts or pieces to understand this model right now. So what sum of squares means is whenever you build a model, right? It's a model. Models might not be accurate. If you build a model which exactly fits to your full data set, then you're overfitting it, and it's not a generalized model, and therefore whenever you get a new one, you will have to rebuild the model. You cannot essentially use it for prediction. So that's why in stats you simplify the models, and one of the simplest models for categorical variable is ANOVA, and for continuous variables is linear models. So within ANOVA, what we do is even like this is true for any modeling, is you have a theoretical model based on your equation. You have a theoretical model, but your actual data may not exactly fit to the model that's being built. And there are differences in the data. What the modeling does is it does its best to fit the data, while not doing overfitting, that is not meeting every point in that model. It tries to build a generalized modeling. And what we have here is, if whenever we say sum of squares, it's basically the difference between your actual data point and the model. As I told you, the model may not be exactly passing through your points. It might be slightly far away. And so there is a difference, or there is an error that needs to be calculated. And this will be more clear. ANOVA is probably not a very good example to explain sum of squares. I'll explain this more clearly in the linear modeling part of it. But for now, just remember that sum of squares is the error between your model and your actual data point. So why do we do sum of squares? Why do we even square that error? So we square that error because some errors might be negative and some might be positive depending on where your model is. And therefore, in order to remove all the negatives, we square all these numbers. So positives will remain positives and negatives will be squared, and therefore they'll be positive. So, and what is residuals is, after you take into account the modeling, whatever number is, whatever values or whatever variance is left, that is going to be your residuals. So don't panic if you cannot get these concepts right away. It will be more clear once we go through the examples. So this model, when we just print this model out, right? It's just going to have this information. But if you do a summary of this, summary of AOV model, you will get different things. That is, you will get the actual variable that you have been using, the two variables that, so this residuals is being created for every model, even if you don't have it in your actual equation. This residual means whatever is left after this variable has explained the variance in your data. So what it has is, this is the variable that we have used for prediction, and we have the degrees of freedom. Degrees of freedom is actually mostly, it's one number less than the number of factors you have. And since our number of factors, we were using 6 sprays, it's the number of degrees is 5. But we do not really use this practically, so forget about that right now. We will come back to it later. And this is the sum of squares that you've seen above, and this is the mean of squares, and this is the f value. So I'll explain these values and what they mean towards the end of the class. But for now, what we do is when we do this modeling for multiple things, suppose we have an equation, like if we had something else to predict it, or maybe a bin number. So we have, say, bin number and something else that we are using within the equation as predictor variables. Suppose if we have two or more predictor variables and we are using it in the equation, we could actually do this with the linear modeling. I'll show you that in a bit. Then for every one of these predictor variables, it's going to be listed over here in the summary. And what we see is this symbol over here. So what this means is the p-value significance. So the p-value significance, if you can see, it's less than 2 to the 2 times 10 to the e to the minus 16, which means 0.16 zeros and a 2, or 15 zeros and a 2. So which is very significant, right? And the 3 stars over here indicate just a graphical representation of the significance, and you'll see that these are the codes. If it's 0 or very close to 0, it's going to give you 3 stars. If it's 0.001, it's going to give you 2 stars, and 0.01 1 star, and it's going to give you a dot if it's 0.05, and if it's greater than that, it'll give you nothing. So you see that, right? So what we are seeing here is what this p-value means is the effect of the spray, the category, is very high on the number of counts. So that's not something that's not news, because this data set is based on the number of counts and the spray names. So obviously the type of spray will have effect on your the counts, or the bug counts. Suppose if somebody gave you this data and they didn't really use any sprays, somebody gave you some data and they didn't really use sprays, maybe they used water in all of these 5 or 6 sprays, and they gave you some data, it's going to be random, meaning some bugs will die, some bugs will end up increasing in number based on just the random what randomly happens with the bugs. And you might not notice any difference in these in those different labels, even though they are labeled, but because water is being used. So at that is the time when you will see basically no significance over here, which means spray cannot define the type of spray you're using, cannot define the number of bugs you have in that experiment. So we always check for this to make sure that your predictor variable actually has some effect on your response variable. So and if it is this significant, obviously we are going to further analyze the data. If there is no significance over here, then we'll probably say your data is messed up, or maybe you're not running the experiment right, or something like that. All right, so let's go to the next part. So specifically for this data set, what I want to show you is how will we know? So this one, what it says is, if you see the summary, it's saying that the whole spray variable, be it any spray, the whole spray variable has an effect on the response variable, on the number of counts of bugs. But we are not able to see any difference between this the different types of sprays. So you have to further dig into this model, and this is something where you use you further dig into this model and you try to see the differences between these spray types. So what you use here for specifically for ANOVA is model.tables. That's the method you use, and you give it the ANOVA model, and you have to define the type. So there are 2 types here. One is the type effects and the other is the type mean. So we'll see the difference between the two. Let's go back to our studio. I just had the bin number as an example, but let's just do model.tables and comparison. Oh, okay, so this didn't run, so that's good, because if I had changed the model and I'm using the model in model.tables, it's going to be different. So this is our initial model, and this is what you get for the effects. So what does effects mean? Let me explain that to you by first showing you the means model table. So whenever you do the type means, you want to see how these means are different between the various categories. So what you see here is a table of means. You have this grand mean, and you have the means for each different sprays. So what does it mean? For the spray A, everything that's tested is having 14.5 bugs on an average. On every box the A spray is sprayed, you see 14.5 bugs, and for the B spray you see 15.33 average number of bugs, and for the C spray it's 2.08, D spray it's 4.9, E and F. So but the grand mean, that is for all the data, not a mean of the means, but for all the data, you see that the grand mean is 9.5. So how do you even analyze this? We want to see how each spray performs compared to the grand mean, right? So what is the difference between the grand mean to spray A? So it's about 5 bugs, and grand mean to spray B, it's about 5.8 bugs. So that's what you see in the effects. It's just the difference between the each category mean to the grand mean. So you see all the difference here. So the difference between 14.5 and 9.55 as bug A effect, and 15.3 subtract 9.5, you'll get that. So from the effects, you will see right away which is the most efficient, or which you want to pick. So from this differences, which one would you likely go with? Which spray do you likely go with from these differences? So on an average, spray A gives 5 bugs more than the total mean. F, so you want to go with you want to pick a spray that gives you 7 bugs more than the grand mean, than the average. CDE. So that's right. So CDE actually mean that you're getting lesser number of bugs than the average bugs, average count of bugs. So that's what we want to look for, right? You want the sprays to be killing the bugs. So you will actually pick something that kills the bugs most, which means you would probably go with C, which gives you on an average 7.4 bugs less than the grand mean. So this is probably the one which you want to go with. And depending on the pricing, you will see, so all these 3 CDE give you lesser number of bugs compared to the grand mean. But depending on the pricing, if you want to compromise a little bit, if you think 7.5 is very close to 6, so, and if spray E is cheaper, you might go with this. Or if you want to compromise the performance more, you might go with this if you're getting it really for cheap. So that is pretty much the ANOVA part of it. And you can basically put stats around it. So here you will visually see the differences and the effects, right? But in statistics, nobody will trust you if you don't have stats around your numbers. So you'll have to put stats around your numbers. So for that, what we do is we use this two key honest significant difference test. So we want to see, so what this says is, you visually you can see that, you know, C is the best, or yeah, C is the best, or so statisticians basically ask this question of, you know, how do you know that C is best, or C is, maybe it's dependent on your sample size, or maybe if you had hit the C spray on 100 other boxes, you might get a different answer. So depending on the sample size, maybe C is different, or maybe C is not very different from D and E. So things like this have to be answered. Therefore, we do this honest significant difference test. So what this does is, basically this is also a built-in function within R. So you do this two key, where is that? Yeah, two key HSD, which is the honest significance difference. And what you see in this is just the comparisons of the, this is basically your total look at the data of what the lower ceiling, the lower floor of this data is, and what is the top, what is the highest ceiling of this data. So on an average, you see the difference between the averages is, so sorry, I didn't explain this part. There, it basically does the difference between each and every spray. So B compared to A, the difference is the difference between the means is this. What you see is this is the lowest number, the minimum, and this is the maximum number depending on your data. And this is the p-value of the difference between the two. So what this p-value says is A and B are not much different. So from your means you find a difference. Statistics says based on the sample size, the two are the same. So similarly, I just explained one part, but there are comparisons for all of these. So depending on which two you want to compare, you have to look at the p-value and see if the difference between those two is significant or not. And there is a very nice way of plotting this. It's this plot where it plots the comparisons or the range of what you see. So if this is the plot, so what you see is the difference between B and A, it falls. You have, this is the mean, that is 0, which is 0 means there is no difference, right? And then some of them fall below 0 and some of them fall above 0. Based on the data points. So these are something, these are something, if it falls around the 0 line, they are comparable, meaning there are some sometimes when both are the same, sometimes when one is better over the other. But if they're outside the 0 line, like this group and this group, it means that one is significantly better than the other, correct? So which means, at least in our data set, there is no data point where you can see C comparable to A, meaning the difference between these two is not 0 anywhere. So these are the two lines. So you can get a quick glimpse of, you know, what's going on and what's the difference between these sprays, these categories. All right, so let's go to linear models. So as I explained before, as I wrote here, these 2 points are for AOV. I hadn't mentioned that, so clearly I just put down that these 2 points are for AOV, meaning the factor or the predictor variable you're using, such as the spray names, have to be a factor or a categorical variable for us to use the analysis of variance modeling. But in the beginning of the class, as I told you, if you have a continuous variable to predict the data, continuous variable to predict the outcome, we use a linear model. So let's get back to our MT-CARS data set. So just for an example of linear model and what you have, and just to get an idea of what it is, I have an simple example here. What it says is, sorry, the number of ice creams sold depending on the temperature outside. So it's basically, you see that as the temperature outside increases, the number of units of ice cream sold also increases. So if you were to draw a line between all these circles, which are the data points, it is kind of an increasing line. So with an increasing slope, meaning as the temperature rises, the number of ice cream sold is more. So this is one typical scenario where you would use a linear model. And this is also a good example of how your linear model will look like. Your linear model is basically this line. If you go back to the point where you learned, lines and linear equations and your graphs, you would try to recall that this line has an equation, right? You have a slope to it, you have x variable, so y is equal to mx plus c. If you try to recall that, that is a linear equation. So this line has a slope which is m. It cuts the y-axis at some point, which is called the intercept, and that intercept is c in the equation. And you have an x values which are variable. So y is equal to mx plus c is the linear equation. And that's pretty much what linear model tries to use when it's fitting your data, when you're using a linear model to fit your data. It's just trying to draw this line, position it based on your data so that your error value is the least. So within the model, what it tries to do is it tries to move this line up and down just to find out where your error is lowest, and then it will find a line where your error is the lowest. What is the meaning of error? So when I told you the sum of squares, right? So this is the line, or this is our model, our linear model, and then the real data points are actually around this line, and there are only like 2 or 4. Maybe this line slightly touches the line, this one, and this one, where the line actually passes through these points, and some are far from the line, like this. So some might be far from the line. The line might exactly intersect a few points. And this is a linear model. And when you see the difference, the distances between this line and this point and this line, and every point and the line, you will arrive at something called error, right? And the difference between this point and the line will be negative. This point and the line will be positive. So this negative lines, when we try to sum up all the errors, this negative will cancel the positive, and therefore we square the individual errors to be able to exactly measure what the error is. We square these individual errors, so negatives become positives, and then we sum up those errors. So that's enough of linear equations, but let's go into this example. What we are trying to do here with MT-CARS is we want to see the influence. I know there are a lot of other factors, right? There are a lot of other factors. You might actually try doing ANOVA with the categorical variables and see over car mileage and see if you can predict anything. So I will actually send you that as the assignment too, so you could work on it. And so in this example, what we are trying to do is we are just using the weight which is a numerical continuous variable used to predict the car mileage. So what we know is we know that there's an influence from our previous um, models and from our previous sessions. We know that the car mileage depends on this weight of the car, but we have to predict how much influence that is using these linear models. So in linear, to make a linear model, the function is LM, just LM, as simple as, you know, AOV for the analysis of variance. Just LM, it's a built-in function. You can use that to write your model. And again, your model has to have a y variable and an x variable. So our y variable here is the MPG, because we want to predict that based on a predictor variable, which is the weight. And you give that equation within the LM function, and give the data set. So what does this give us? Let's go back to our I don't have that, so let's write here. So let's make a linear model. Use the LM function, MPG tilde weight, and you have to give the data set, empty cars. So now the model is built. So let's see what is in the LM model that is built. So as you see, it's the similar thing that you saw for AOV, and you have the actual function that we used, the equation, and then what you have here is coefficients. So coefficients with an intercept and weight coefficient. So if you go back to your y is equal to mx equation, what the intercept is, it's the c, which is, it's the c, which is a constant, and this negative 5.3 is the coefficient for weight. So this is the slope, this is the m, and weight is going to be different based on which car it is, and y, which is our response variable, is going to be, which is our MPG, is going to be different depending on what weight is. So now it built an internal linear model with these coefficients, and this is what it's giving us. So let's look at summary of this. What does it give us? So it's giving us actually a lot of things here. First, we are getting residuals. Residuals is, as I told you, after weight predictor value takes care of some variance in the data. Whatever is left is the residuals. So usually what we do, I'll tell you a practical example that we use. Whenever we try to analyze data, any data for that matter, any experimental data, we first adjust the data for certain technical variations, such as the batch number or the processing date, or if we know that different people processed the experiments, we will try to adjust this based on the processor or the experimenter, whoever has done it. We'll try to adjust it for that first, meaning we'll put that technical variables as the predictors and adjust this data, and then use these residuals. That means we adjusted the data already. Use these residuals for further analysis. So just a practical example for when we use residuals. But here, since we are not doing any more analysis on this, if you wanted to remove weight from this, say you already know that, you know, weight is one important predictor within of mileage. You want to see what the next variable is, or how much the next variable impacts. Then you will use this residuals and run this residuals on another variable. So stepwise, if you want to remove the effects of one and test the effect of another variable, this is what you will take of the residuals. So let's go into what these coefficients are. So coefficients, pretty much we showed you, like in the previous one, we have intercept and we have weight. Since this is a linear model, we don't have residuals in this, but we have just the intercept and we have our variable weight. So what we are seeing here similarly is we see the p-value, and the p-value, the significance code gave it 3 stars, and this also gave it 3 stars. So essentially, so the intercept pretty much always has stars because the intercept is a constant that is being added to every data point. It pretty much has more significance in predicting the output. So don't worry about the stars, but the important part is to look at weight. To look at weight and whether it's a predictor. Suppose if you used some other predictor variable, like color of the car, or color of the car to use to predict MPG, it might not have any correlation or any value or effect on the mileage. So you would think that based on color, you can't really predict the mileage, and therefore, if you use color, this significance will not show up. Meaning, you cannot really. There is not really much relationship going on between color and the output variable. But again, color can be categorized, so this is not the right modeling to use. It's going to be A or B, but you could think of something else like that. Maybe a manufacturing number or something like that, some random continuous variable. So any questions until now? I know I'm going in a flow, so I wasn't asking for questions, but let's proceed with the next one. So if you want to just get coefficients, or you see that with the summary, you are able to see all the details of the model, and you have all these details. You have residuals, coefficients, etc. But there are lots of other methods that you can use on this model to extract each of these pieces. So one such method or function you could use is the coef, which extracts coefficients in the model. So our coefficients in the model are just intercept and weight. So you could extract those, and so just try to plot this. So plotting is a bit cumbersome for plotting the linear model. There is not a direct function which you could use, and I'll in a bit just show you what will be plotted if we just did plot of the linear model. It's going to be lots of plots, which I'll show you. So if we just run this, what it's going to do is hit return to see the next plot. So hit return, and the first plot that you'll see is this one. What it does is it plots the residuals versus fitted values. So we check all of these for checking if there are any abnormalities in the data. So for now, let's just skip this, go to the next plot. So this you have seen in the last class. It's a QQ plot, and just to see if your data fits a normal distribution, you want to be able to see this. You can see that some outliers over here, Fiat, Toyota, and Chrysler over here, but others pretty much follow this theoretical quantile normal distribution. So that's something. So to see the next plot, just hit return, and you will see again this is some other QC plot, So let's not go into the details of this. And the next plot, again, one of the other QC plot. So in most of these plots, you see that this is a Cook's distance. You see that these three are to be outliers. So if you just did a plot of the linear model, that's what you'll see, the series of plots. If you want to actually plot that linear, that line, or increasing or decreasing line, you will have to do it the conventional, typical, more cumbersome way of giving um, the equation, the actual linear equation within plot. So give it this whole equation within the plot, and yeah, so it's going to just draw, it's just going to be a scatter plot of these data points, but you still want the line um, which shows the model, right? So what you do is you do an AB line. So AB line, usually AB line is something you want to check help on it. It's basically a function to draw a line anywhere on the plot. So you could actually give it like coordinates, and you could specify how much to move from the left and right, and different things. But here we'll have to do an AB line with coefficients. So you should actually give it the coefficients. So you will give it the coefficients of the linear model. So you could either do this, or you could do the coef, which extracts the coefficients from the linear model, and our linear model is this one. So what you're saying is you're giving it a y cut, which is the intercept cut, and you're giving it an x slope. So if you draw this, then it will draw this line. You see this line over here, right? So this line is our actual model. It's kind of cumbersome, these two steps to draw this line. So this is our model. So this is based on the y-intercept, I think, is 30 something, is a 30 something. Yeah, it's 37.2, and this is the weight is -5. So depending on, so that is 5.3. Yeah, so that is, depending on these two, it's going to put this line. It has to put it at 37. Let's see if in this it put it. Oh, and this also it's putting at 30. So the intercept has to be at 37. I don't know why. So I'll check that once again to see why it's starting at 30 instead of 37. It's supposed to be, the intercept is supposed to be the point where it cuts the y-axis. And this is supposed to be the point, this is the minus 5.3 is the actual slope of this line. All right, so there are a series of other functions you can use to extract information from this linear model. Like coef we already saw. So one is conf int, which is the confidence interval that will retrieve from the model. Fitted is the way you can get out the fitted values, meaning if those values were um, actually lying on the model, what those values will be. And residuals, as the model, the summary of the model shows, residuals are the difference between the theoretical model, your line, and your actual data point. And there is a covariance matrix that you can retrieve. And so there are lots of these functions. So here in this last slide, I just have an explanation of of what your summary means. So most of it I've already explained. But this last part is something that I missed. So you see this last one, which is called the F statistic, and you have the F statistic and a p-value. It basically, this is from the F test. So it basically explains how your model, if your model explains a significant portion of the variance in the data or not. So as I told you, if you were using the color and for or some other continuous variable, maybe the manufacturing ID of the car to predict the mileage, this one will have a very low p-value, and this will also have a very low p-value. So basically, it's saying that so since we have the weight here, we are able to, this significant p-value on the F statistic means that we are able to explain most of the variance in your data by using this weight as a predictor variable. And you can compare this if you want to compare how much of variance is explained by different variables. You can build different models using different predictor variables and compare this p-value and see whichever has the strongest p-value that will be able to explain most variance in your data. So that's pretty much the end of today's session. Anybody has any questions?